Okay, welcome back to learnpiezo.org. We're continuing on forward with low power testing. If you can remember, in part E, we discussed programming in quite detail in order to determine the impedance, the absolute impedance, versus frequency. And we can get a lot of understanding about how we designed this transducer and system using it. F. Next part was F. And F, we quickly described how do you assemble this. The important parts are you have to use weight, pressure. You have to put that weight on top of the epoxy, use the right type of epoxy, make sure you sand down the paint can in order to get good contact with the epoxy, and that's about it for, and you have to let it set overnight. It's important that you put weight. I think I put about 20, 25, almost 30 pounds, I think I put on that little transducer. So that must have been about maybe around 10 pounds per square inch, or maybe about 6 or 7 pounds per square inch. I put. Now we're in part G. And in this part, we're going to use this program, and we're going to use it with the assembly, which is our device, and we're going to test it, and we're going to display it and discuss the results. So here are the results. Bam! I know it was quick, but here are the results. This is the impedance. I can't really write that well sideways, but I can sure try. And it's typically written as and the units are ohms, and this is a log scale if you notice. This scale is in frequency in hertz. Hertz, so 2 pi f. So that's how you get frequency. Anyways, you don't have to do any calculations because this would have come out to you. So this is 3.5 kilohertz, no, 35 kilohertz, 40 kilohertz, 45 kilohertz, 50 kilohertz. So we see our region of interest of here, right here. So I'll start by bringing your attention toward certain facts. We start with our free transducer, which we have a resonance frequency here, and a little messy anti-resonance, but you can tell it's about right there. There's other resonant modes occurring, which is then harming its operation. Not harming, but skewing its operation, because it's only harming if it's happening near the resonance frequency. As soon as we attach it. Now, unloaded means it's attached in the assembly, but it has no water inside. So the resonance frequency shifts lower because when you attach that piezoelectric, device to the big paint can, there's a lot of the bottom of the paint can is allowed to move with the transducer, and because you're actually effectively increasing the geometrical size, you are then increasing or decreasing the resonance frequency. Once you increase size, you decrease resonance frequency. Also, some of the modal activity may have been changed due to the sheer, the epoxy and that contact. But essentially, when you get more mass or when you become of a larger size, you decrease resonance frequency. So that has a small, a noticeable effect, though. You also what happened when the anti-resonance shifted down as well, and I'll discuss the significance of anti-resonance soon. Then what we saw when we filled the transducer, it increased its resonance frequency. It wasn't as high as that of the free case, but it still had an increase in the resonance frequency. The anti-resonance frequency was sort of, where is it? Where can you see here? Let's just erase all of this. The anti-resonance frequency is about right here. So it still has a lot of noise. I'll draw that in blue so it's less confusing. So if you want to just make everything more clear, that's that one. And this one, we just have something like that. And for the red case, we have, the loaded one, something around there. So Those are the results. These are the results. So now what do they mean? What things are we going to look at to understand? And I'll tell you right here what we're going to look at. We're going to look at the resonance frequency, the anti-resonance frequency, the effective coupling factor, the resonance impedance, and the quality factor. All those four things. The resonance frequency is determined by geometry. If you increase the size or the boundary conditions, the resonance frequency changes. So we can see as we went from the free to the unloaded case, we dropped significant resonance frequency. But then we regained some when you inserted the water, which tells me that the boundary condition was not elastic. Rather, the boundary condition was more of a solid condition. So it's more of a clamping type. So when you start to clamp, so when you have this transducer, and then you start to put more water inside of this bucket here, it's sort of becoming a more of a stiff or a large mass, which eventually that mass acts like a support which cannot be moved, in which case the resonance frequency would decrease. Now we have our anti-resonance frequency. Now this is very important. The anti-resonance frequency depends on the ratio between electrically active or piezoelectrically active material effect and the original resonance frequency. And it relates to both the clamped capacitance and the free capacitance, and that discussion is done somewhere in one of the lectures where I discuss anti-resonance. You can search that, YouTube, anti-resonance piezoelectric, or anti-resonance learnpiezo.org. Search that on Google, you'll find it. So this tells us sort of that effect of the electromechanical coupling, but it's also related with the resonance frequency, so it scales properly. What's more interesting in how to interpret this value, as you can see it changes approximately with the resonance frequency. What's more important to determine the effective coupling factor, and it's sort of a ratio. This should not be 1, by the way. This should be 0.28, sorry. It tells you the effective coupling factor, which is the effective amount of piezoelectrically active system. So if you have a high coupling factor, you know that your piezoelectric material is coupling very well with the outside environment, and there is not much inactive material, meaning metal, around. So if there's more piezoelectric material, you're going to have a higher coupling factor. If there's less, you're going to have less. And the better and so that's one point. So the coupling factor in broad terms, speaking very generally, it depends on the amount of piezo, and 2, the coupling of piezo. So here, this right here where I have the free and unloaded, they seem to be pretty much the same, which is not true because the anti-resonance frequency for the unloaded case was not very well defined. What's more important is, so this 0.2 difference is not really significant, but this 0.1 difference between the 500 ml case and the free case is significant. And sorry, I forgot to mention the equation for a coupling factor, which is the FB squared minus FR squared, all divided by FB squared. And this gives a general understanding of the coupling. And you have to put that all under square root. And then you have the effective coupling factor. This term generally, for this case, is an effective coupling factor. For other geometries, you can analytically calculate it, especially for geometries where the piezoelectric material is the only thing there. So we have this significant drop. And what's the significance of this drop? Why does it drop? It's because there's a lot of inactive material. Okay, there's a lot of inactive material, and it is reducing the coupling. And is that a bad thing? No, it's a good thing. It's a good thing to see this. And the reason it's a good thing to see this is because we know that our piezoelectric material, it's coupling with the outside. But in terms of coupling with the outside, it reduces the relative amount of piezoelectric material. Right? So because if it didn't couple well with the whole system, then we would essentially see this transducer vibrating free, or vibrating similar to the unloaded case. But because by putting water you change the system, it means that the transducer is affecting the water, and the water is affecting the transducer, which is great, which is what you want. Now the whole worry here is that, is my transducer actually gonna propagate waves? I know it can vibrate, but is it going to propagate waves through the water? Is that coupling good? Did the epoxy work? And I think this is a very strong case that the epoxy worked, and that when we're going to increase the power, which we're going to be doing the next, not the next, but something soon, we have a change. Next, I want to draw your attention to impedance, and this is how much effectively how much vibration. This is all, how it is literally the impedance, or the resistance at resonance frequency. But qualitatively, it can be looked at how much current, which corresponds to vibration, how much vibration or current is occurs when you apply a certain voltage. Let's say 1 volt. Here you have a very large amount of current when you apply 1 volt. So let's say V equals IR, and you divide the R on the other side, so 1 volt divided by 20 versus 1 volt divided by 87, which is the next number, 1 volt divided by 52. So here you have a lot of current, a lot of vibration, a lot less, but four times less vibration, and here 2 times less vibration. So we can see here again, the unloaded case probably has a lot of losses because of that boundary condition, or that the dynamic behavior is strongly affected by the epoxy, but not that much, because it's still decently high, not that high impedance. In this case, we have a lower impedance, 52, which signifies that the water is changing the dynamics, which is something that we want to see. Now we want to look at the quality factor, and what's the way you determine the quality factor? I can just go into one of my the way to determine the quality factor, and is this. Well, I'll explain how I did the experiment. I forgot to mention. So this is an image of the course spread. So I did approximately 30,000 kilohertz to 50,000 kilohertz in steps of 100. And in the other case, I found the resonance frequency from that CSV file, and then I did sweep 500 hertz less to 500 hertz more of that resonance frequency. So I did that in 1 hertz steps, and that is the data which I used to calculate, and I used to get the impedance, and I used to get the quality factor. So I did a very coarse sweep. I did 2 sweeps in my data. I did 1 coarse, and I did a second fine sweep around the resonance frequency, and this is around 30K to 50K, and this is around the resonance frequency in steps of 1 hertz, in steps of 100 hertz. So I had 2 files, and I used that second file to determine the impedance accurately and the resonance frequency and the quality factor accurately. So the quality factor is determined like this. So I think I may have already explained it, but for your benefit, I'll do it again. And for your benefit, I'll also try to write more neatly. Sorry about that. So the quality factor is determined. First step, you find the minimum resonance. Oh, and sorry, this is actually all covered in the impedance analyzer lecture. So go to the impedance analyzer lecture of learnpiezo.org. It's one of the lectures with PowerPoint and also practical demonstration. Go to the PowerPoint, look for the quality factor determination. Essentially, the quality factor is telling us how lossy of a resonator is our piezoelectric device. And when the piezoelectric material the device is by itself. It has a very high quality factor. It vibrates a lot, very with less dissipation. When you hook it to the loaded case, it vibrates much less, about 3 times as less, for the same given voltage at resonance. But when you put the water, it seems to be vibrating more, not as quite as much as the free case, but more because the epoxy, which is a very lossy material, it has a lot of loss, a lot of dissipation. It is less of the dynamic in the water, and the weight increases the stiffness of that and the mass of that boundary condition, therefore making it seem more like an infinite mass at the end of the transducer, thus increasing the quality factor. So I want to end this lecture by giving the final takeaways. 1. Resonance frequency was affected by assembly and water. The coupling factor, it reduced with water, and that tells me good coupling. And that not alone tells me good coupling. I look at the other factors here, and the other factors are that the impedance is similar. The impedance is similar between the 3 cases. On similar meaning on the same order of magnitude, so it tells me that something didn't horribly go wrong, that the impedance became 1000. That means the transducer is not able to vibrate. The resonance frequency is completely shifted and the dynamics are completely changed. But now the dynamics are similar, except the boundary conditions vary slightly in order for us to propagate waves through the water. Next is that the quality factor is less with assembly, which tells me that the epoxy is doing its job. That epoxy is affecting the dynamics. It's actually adhered quite good, or else you wouldn't have much effect from the epoxy. And it recovers slightly. It recovers with adding the water. So therefore we get the very important part that the water affects dynamics, and this is a really good sign that our system is working. How well it's working, this is my first prototype of an ultrasonic cleaner, I don't know. But what we're going to be doing in the next lecture is we're going to devise ways of driving with high power or high voltage. Right now we're driving with 2 volts. Most of that 2 volts is dropped over the 325 ohm resistor, which is being used for measurement of current. Yeah, we could use a smaller resistor, have more of that 2 volts over the transducer, but we're really looking at more than 100 volts of drive for this thing. And that is when we're going to start hearing that classic noise and all of the different dynamics. So I'm going to try, and we're going to work with ways to do that. There are several ways to do it. I'm going to try using an audio amplifier with a transformer. The second thing I'm going to do is I'm going to use the outlet energy. So we have a little outlet, wall outlet, and that's in America. That's going to be 120 volts at 60 hertz, and we're going to try to use that directly. We're going to make it into a 120 volts DC using a rectifier, and then we're going to give a probably 1-to-1 isolation, and then well, I would actually probably do 1-to-1 isolation first, and then go ahead and use the rectifier. After doing that, what I want to do is use that DC voltage in order to pulse that DC voltage using a microcontroller and a MOSFET. Microcontroller and MOSFET. And that MOSFET or a solid state relay, in order to effectively drive this ultrasonic cleaner. Alright, thank you for watching this video. I hope you understood some of the methods used to understand and collect data. To recap, we collected data like this. You can stop your video. We got this at the end, but we also got finer data, which I didn't show. Fine, frequency response data, which I used to determine the impedance and quality factor on resonance. I got these values, and furthermore, I discussed the effective coupling, which was reduced, which is good because we have less piezo there now. So just because the coupling reduced doesn't mean that you don't have good coupling. It's just that you increase the amount of other stuff there. Therefore, you decrease the amount of you decrease the amount of coupling. But if we, for example, if you move the piezoelectric discs off of the nodal point of the transducer, then the coupling would decrease and you wouldn't be adding any more material. So there's also that case where you can have less coupling and the same amount of material, same amount of piezo and the same amount of other stuff. So hope that all made sense. Please shoot me an email. You can find my contact information at learnpiezo.org, and you may ask whatever you will. Thanks for watching.